And then we use our base to reattain aromaticity. Before we even look at that, let's look at some resonance structures. So if I took this molecule and I were to draw resonance structures, and I'm going to keep drawing them, and you want to practice drawing resonance structures from organic 1, I end up with a positive here. Can I get that? Let's draw another resonance structure. Notice that the electron donating group by resonance is contributing to the resonance structures and helping to stabilize. So we end up having a secondary resonance. And the secondary is based on not the resonance in the ring, but the fact that we have an additional resonance structure that's associated with the substituent on the side. And I can draw more resonance structures. Another one would look like this. And so essentially our 3 best resonance structures that I have are 4, sorry. These are pretty good resonance structures. Some of these are under the octet. This one has a plus on a electronegative element. So they're not the most wonderful. That's why the next step is going to happen, which is the base coming in and deprotonating and reforming your aromatic molecule. However, it's not really that part that is the driving force for what we're talking about right here. So let's talk about this from the meta, and we're going to compare. So I'm going to draw the resonance structure as a consequence of adding in the meta position. And so let's go ahead and draw some resonance structures, and we're going to see what happens. And so notice that when we try to draw these resonance structures, we are unable to use that electron donating group to help stabilize. So we actually end up with more resonances here in the ortho, and the para position is what you're going to see. I didn't draw the ortho, but the ortho does the same thing. And so that electron donating group adds a secondary resonance, and that secondary resonance adds more resonance structure, stabilizing these resonance intermediates, driving the reaction to do an orthopara. Now we get resonance stabilization in the meta, we just get less resonances. So this is a second explanation for why the donators are giving ortho and para. Now, for the electron donating group that are alkyl groups, so when we have alkyl, we don't have resonance, but we still do have hyperconjugation. And that hyperconjugation is donating electron density to the plus charge to stabilize. And so even though there isn't an extra resonance, we do have stabilization because the positive charge is stabilized by alkyl groups. Now, what happens with electron withdrawing groups and what's going on there? And later on we'll talk about what happens when we have multiple groups. So let's use the electron withdrawing group nitro. All right, and let's add in the ortho. Let's do the para position. And then we'll do the meta position. And again, ortho and para is going to do the same thing. So we're drawing resonance structures of the rhenium complexes. And let's do the meta. And compare. And if you already take one quick look at the previous resonance structures, you should notice one thing that you learned about resonance structures in Organic 1 that is a problem. And we're not going to see that in the meta position. So if you look very carefully, in Organic 1, we talked about having 2+ charges next to each other is kind of detrimental for resonance structures, because there's going to be, if we think about Coulomb's law, there's a conflict here, and they're not stable next to each other. So this resonance structure is not likely. Doesn't mean it's impossible, it's just not likely. And so you're kind of going from like 2.1 resonance structures to 3 resonance structures, so these resonance structures are less stable. So it turns out, for the kind of opposite reason, electron withdrawing groups stabilize at the meta position because one of the resonances are unstable in the ortho position. So thinking up through the 2 reasons why we get the direction that we get, we have the original resonances that put, for electron donating groups, the negative on the ortho and the para position, and secondly, the secondary resonance stabilizes the rhenium complexes, or if you're talking about alkyl, it does this by induction. If you're talking about electron withdrawing groups, the 2 reasons are, for the original structure, the negative, there's a positive charge on the ortho and para, which leaves meta more nucleophilic. And the second thing is that the secondary, so I should have said secondary resonances on ortho and para are stabilized. and the secondary resonance on the meta is more stable with 3 resonances that are pretty good compared to ortho-para that has 3 with 1 very poor contributor. So those are kind of the ways that we look at that. Now our last thing that I kind of mentioned, and we'll get back into that, is if you're talking about having multiple things on the ring, as you saw in your reading, multiple groups on the ring are going to go by a couple of different things. So the more strongly donators, and this is where we're now going to have to go and figure out what's the strong versus weak. So we kind of briefly talked about that in Organic 1 as well as this semester, but now you really want to focus on strong donators. So the more stronger one will dominate if they're opposing each other, and if the directing effects are not opposing each other, then you don't really have a problem. So it's only when they oppose each other. So depending on what it is, the stronger donator is going to dominate. If there is only withdrawing groups, the weaker of the withdrawing is going to make an effect, because remember, the stronger the donator, the more it will counter the ortho-para effect.
In the previous unit, we had this reaction in which I said that we always add the diazonium salt into the position opposite to the OH, but it's because the OH is an electron donating group, and by resonance helps to support this group going in the para position next to it. We also saw something like this when we looked at the beginning of this chapter and saw the reaction for the thyroxine producing compound where the iodides were going in the ortho position on the molecule.